Find somewhere comfortable, somewhere the weight of the day can finally set down beside you. You don't need to follow any of this closely. You don't need to hold on to it. The words will arrive on their own, and if some of them drift past without quite landing, that is perfectly fine. Tonight we are going somewhere quiet and vast and ancient, into the heart of matter itself, into the smallest things that exist, into particles so shy and so numerous that they have been passing through your body every second of your entire life without you ever once feeling them. You have never felt a neutrino, no one has, and yet they are here, right now, threading through you in their trillions, through the bed beneath you, through the floor, through the earth below the floor, emerging on the far side of the planet and continuing outward into the dark, without pausing, without slowing, without leaving any trace that they were ever here at all. That is what tonight is about. A particle so small, so neutral, so utterly indifferent to the world of solid things, that for 26 years after it was first imagined, no one could prove it existed at all. The man who dreamed it up was half convinced it never could be found. And yet it turned out to be one of the most abundant particles in the entire universe. The universe is practically made of them. So rest now. Let the words come and go. We are in no hurry tonight, and there is nowhere else to be. In December of 1930, a physicist named Wolfgang Pauli sat down and wrote a letter he addressed with a certain gentle self-deprecation to a group of colleagues attending a conference in Tübingen. He called them, "Dear radioactive ladies and gentlemen," which already tells you something about the man. A brilliant, restless Austrian, known for being able to identify a wrong answer faster than almost anyone alive, and not always kindly about it. But this letter was different. This letter was humble, almost apologetic, because Pauli was about to propose something he wasn't entirely sure he believed himself. He had a problem, a real one, and it sat at the very center of the laws of physics. The problem was called beta decay, and to understand why it troubled him so deeply, we need to sit with it for a moment. Beta decay is a kind of radioactivity, a process that happens naturally inside certain atomic nuclei when they are in an unstable configuration and need to shed some energy to settle into a more comfortable state. In beta decay, a neutron inside the nucleus, one of the heavy neutral particles packed into the center of every atom, transforms itself into a proton. When that happens, the nucleus gains a positive charge, and to balance the books electrically, it spits out an electron. That electron flies away from the nucleus at high speed, and in the early days of nuclear physics, physicists called it a beta particle, which is where the name comes from. Now, the laws of physics have a very firm rule about energy. Energy cannot be created and it cannot be destroyed. It can only move from one place to another or change from one form into another. This rule, the conservation of energy, it has never, in any experiment ever performed, been found to be wrong. So when a neutron transforms into a proton and an electron, you can calculate precisely how much energy ought to be released. The neutron is slightly heavier than the proton, and that difference in mass, because mass and energy are related, as Einstein showed, has to go somewhere. It should all go into the kinetic energy of the electron flying away. Every single electron from a given type of beta decay should therefore carry exactly the same energy, the full share, every time. But they didn't. When physicists measured the energies of the electrons coming out of beta-decaying nuclei, they found a continuous spread of values. Some electrons came out fast, carrying nearly all the expected energy. Some came out slow, carrying almost none. Most came out somewhere in the middle. It was as though the energy was being divided up randomly with no consistent rule, and the total was always less than it should have been. The missing energy simply vanished. It was not in the electron. It was not left in the nucleus. It was not detectable anywhere. For many physicists at the time, this was genuinely distressing. Some began to wonder whether energy conservation might simply break down at the scale of the atomic nucleus. Niels Bohr, one of the giants of early quantum theory, was willing to entertain that possibility. Perhaps energy did not always have to balance. Pauli could not accept this. He found the idea of abandoning energy conservation almost physically uncomfortable. And so, in that December letter, he proposed an alternative, a desperate remedy, he called it. What if the energy wasn't missing at all? What if it was being carried away by a particle that no one had detected because it was so nearly impossible to detect? He imagined a particle that would have to be electrically neutral, otherwise it would leave an electromagnetic trail and someone would have noticed it by now. It would have to be very light, lighter even than the electron, possibly with no mass at all, because the energy accounting only worked if the hidden particle could carry a range of energies without adding too much to the overall mass budget. And it would have to interact with matter so weakly that it could fly out of a nucleus and through any detector ever built without so much as a nudge. Pauli himself was not fully comfortable with this proposal. He wrote to his colleagues that he had done something he wasn't sure a theorist should do. He had proposed a particle that, by its very nature, might be impossible to ever observe. He felt, as he put it, that he had committed a cardinal sin. You should not, in good scientific conscience, propose something that can never be tested. But the alternative, throwing away energy conservation, felt worse, so the letter was sent. For the next 3 years, the idea lived in a kind of informal limbo. Pauli talked about it at conferences, but did not publish it formally. Then, in 1933, Enrico Fermi took Pauli's ghost particle and built something around it. Fermi was an Italian physicist of extraordinary range, the kind of scientist who was equally comfortable with abstract theory and hands-on experiment, and he constructed a complete mathematical theory of beta decay that incorporated the hidden particle as a real, necessary component of the process. He described exactly how the neutron transformation worked, how the electron and the hidden particle were produced together, and how they shared the available energy between them in a way that was random each time, which is why the electrons came out with a spread of values. The energy was always conserved. It was just that some of it was leaving in a form no one could see. And it was Fermi who gave it its name. In Italian, the word for neutral is neutro, and the diminutive ending, ino, turns it into something small. The neutrino, the little neutral one. The name is gentle, almost affectionate, a small thing, a quiet thing, a particle so modest in its interactions with the rest of the universe that Pauli himself, in the years that followed, began to worry it might remain forever hypothetical. He reportedly said, at some point in the 1930s, that he had proposed a particle that could never be detected, and that this was the worst thing a theoretical physicist could do. He was wrong, as it turned out, but it would take 26 years to prove it. What had been established by the mid-1930s was this. Inside every nucleus where beta decay occurs, a neutron transforms into a proton by emitting two things simultaneously. One is the electron, the beta particle, visible and detectable. The other is a neutrino, or more precisely, what we now call an electron antineutrino, the antimatter partner of the electron neutrino, invisible, carrying away its share of the energy, slipping through the walls of any instrument as though those walls were not there. The laws of physics were intact, the books balanced, the missing energy had a home. It just lived somewhere no one could reach it yet, a particle named, described, theorized, incorporated into a formal mathematical structure, and entirely, stubbornly, beautifully unseen. There is something quietly poignant about a particle that everyone believes in, but no one can find. By the early 1950s, the neutrino had been part of theoretical physics for 2 decades. It appeared in equations. It was taught in universities. Physicists spoke about it with the casual confidence they reserved for things they were quite sure existed. And yet no neutrino had ever actually been detected. No instrument had ever recorded one passing through. In the most literal possible sense, the neutrino was still just an idea. The fundamental problem was not a mystery. Everyone understood it. The neutrino, by its very nature, almost never interacts with anything. And that word, almost, is doing a great deal of work. It is not that neutrinos never interact. They do, through a mechanism called the weak nuclear force, one of the 4 fundamental forces of nature. But the weak force is extraordinarily feeble and operates only over distances far smaller than the diameter of a proton. To put a number to it, if you took a neutrino and fired it at a wall of solid lead, you would need that wall to extend for roughly 1 light year, about 9.5 trillion kilometers, before the neutrino had an even chance of being stopped. The Earth is not a wall. The Sun is not a wall. To a neutrino, they are barely suggestions. This is why Pauli despaired. To catch a neutrino, you would need to observe an enormous number of them and hope that, by sheer force of statistics, one of them occasionally flinched in the direction of your detector. The question was whether any source of neutrinos existed that was dense enough and any detector sensitive enough to make that hope realistic. The answer, it turned out, was sitting in South Carolina. Nuclear reactors, the kind built in the late 1940s and early 1950s as the first generation of fission power plants, are extraordinary sources of antineutrinos. When uranium atoms inside a reactor split apart in a process called fission, they produce a cascade of unstable smaller nuclei, each of which is rich in neutrons and eager to shed them through beta decay. Every one of those beta decays releases an electron antineutrino. A large reactor running at full power produces something in the region of 5 times 10 to the power of 20 antineutrinos every second. That is 500 million trillion antineutrinos every second, radiating outward through the walls of the reactor and into the surrounding world. Frederick Raynes was a physicist at Los Alamos who had been thinking about the neutrino problem for years. He was drawn to it partly because of its difficulty. There was something appealing about the most elusive particle, the one everyone agreed on and no one had caught. He initially considered, with characteristic ambition, whether a nuclear bomb test might provide a brief, intense enough burst to be useful. He eventually concluded that a reactor was a better idea. Steadier, longer lasting, and the flux was still enormous, even a few meters from the core. He recruited Clyde Cowan, an experimental physicist with a gift for building things that worked under difficult conditions, and together they began designing what they would call Project Poltergeist. The name was chosen with affection. A poltergeist is a ghost that occasionally, unpredictably, makes itself known, which is exactly what they were hoping the neutrino would do. Their strategy was elegant. They placed a large tank of water near the reactor. The water was laced with cadmium chloride, a dissolved cadmium salt, and surrounded by sensitive light detectors. The recipe was elegance of events. An antineutrino from the reactor, one of the trillions passing through the tank every second, would very occasionally strike a proton in the water, the nucleus of a hydrogen atom. When an antineutrino collides with a proton in exactly the right way through the weak force, the proton transforms into a neutron and simultaneously produces a positron, the antimatter partner of the electron, carrying a positive charge. This process is called inverse beta decay because it is essentially running the original beta decay reaction backwards. The positron, being a charged particle, immediately begins to interact with the surrounding water. Within a few centimeters, it collides with an ordinary electron, and when matter meets antimatter, both are annihilated and converted entirely into energy in the form of two gamma rays, two packets of high-energy light, which fly away from the collision point in opposite directions. Those gamma rays can be detected. But that is only the first part of the signature. The neutron produced in the same collision wanders through the water and, within about a millionth of a second, is absorbed by a cadmium nucleus. Cadmium is particularly good at absorbing neutrons, and when it does so, it releases another burst of gamma rays. This second burst of light arrives a tiny but measurable interval after the first, that characteristic delay being the time it takes the neutron to slow down and find the cadmium nucleus. The beauty of this two-part signature is that it is very hard to fake. The first flash, followed by the second flash, a precise fraction of a second later. That specific rhythm is the fingerprint of an anti-neutrino interaction. Almost nothing else in nature produces it in quite that way. Reynes and Cowan set up their apparatus at the Savannah River nuclear reactor in South Carolina in 1956. They ran the experiment carefully, comparing their detection rates with the reactor running at full power versus the reactor shut down. When the reactor was on, they saw the signature, the paired flashes, arriving with the characteristic delay at a rate consistent with what the theory predicted. When the reactor was off, the signal disappeared. On June 14, 1956, Frederick Reynes sent a telegram to Wolfgang Pauli. It read, simply, that they had definitively detected the free neutrino. Pauli, who was at a conference in Geneva, is said to have responded with great delight and celebrated accordingly that evening. He had waited 26 years to hear that his ghost was real. He was 56 years old when the telegram arrived, and he died 2 years later. He did not live to see the Nobel Prize that would eventually be awarded for the detection. That came to Reynes alone in 1995, 21 years after Cowan's death. But in that moment, in 1956, with the telegram in his hand, Pauli knew. The little neutral one was not just an idea, it was a thing in the world. It passed through walls. It had been caught, just once, in the act of leaving a trace. The poltergeist had finally knocked something over. What Reynes and Cowan had detected was specifically the electron antineutrino, the antiparticle partner produced in beta decay. And at the time, the assumption was simple. There was one kind of neutrino and its antiparticle, and that was the complete picture. The neutrino family was small and tidy. For a few years after 1956, the neutrino sat comfortably in its place in the growing catalogue of fundamental particles. One neutrino, its antiparticle. The family was complete. Physicists had other things to think about. The 1950s and early 1960s were a period of extraordinary activity in particle physics, with new particles being discovered at accelerators almost faster than theorists could name them. The neutrino was caught, catalogued, and set aside. But there was a quiet puzzle accumulating in the background. The electron, it turned out, had a heavier cousin, a particle called the muon, discovered in cosmic ray experiments in 1936. The muon is in almost every way identical to the electron, except that it is about 200 times heavier. It carries the same negative charge. It participates in the same interactions. It decays in the same general manner, producing, among other things, a neutrino. But nobody had checked whether the neutrino produced in muon decay was the same particle as the neutrino produced in beta decay. It seemed like a reasonable assumption, but assumptions in physics have a way of being tested. In 1962, at the Brookhaven National Laboratory in New York, 3 physicists named Leon Lederman, Nell Schwartz, and Jack Steinberger set up an experiment that would answer the question. Their approach was bold in its simplicity. They would create a beam of muon neutrinos specifically associated with muon decay, and then see what those neutrinos did when they interacted with matter on the other side of a very large shield. The shield they used was 10 meters of solid steel. To be precise, it was assembled from the salvaged armor plating of a decommissioned battleship. The beam of particles from the accelerator contained a mixture of things, but most of the charged particles were absorbed by the steel. What emerged on the far side were neutrinos, the only particles capable of passing through 10 meters of iron as though it were a gentle suggestion rather than a barrier. On the far side of the shield, they had a detector, a large aluminium spark chamber, a device that made the tracks of charged particles visible as bright sparks when the particles ionized the gas inside it. The team then watched for what happened when the emerging neutrinos very occasionally interacted with the aluminium. Here is what the theory predicted. If there was only one kind of neutrino, the neutrinos should sometimes interact with a proton or neutron in the aluminium and produce a charged particle. Sometimes an electron, sometimes a muon, with roughly equal probability. If the neutrino from muon decay was the same particle as the neutrino from beta decay, both outcomes should appear. What they saw instead was this. Every single charged particle produced in the detector was a muon. Not one electron appeared. Over the course of months of running, with dozens of detected events, the neutrinos on the far side of the steel wall would only ever produce muons. The conclusion was clear. The neutrino associated with the muon was genuinely different from the neutrino associated with the electron. They were two distinct particles. The muon neutrino and the electron neutrino were separate members of what would turn out to be a family of three. Liederman, Schwarz, and Steinberger received the Nobel Prize in Physics in 1988 for this discovery. The third member of the family, the tau neutrino, associated with yet another heavy cousin of the electron called the tau particle, was not directly detected until the year 2000 at Fermilab in Illinois, though its existence had been strongly inferred for decades before that. To understand why neutrinos come in three kinds, it helps to understand something about how the fundamental particles of nature are organized. They fall into two broad families: quarks, which are the building blocks of protons and neutrons, and leptons, which are particles like the electron that do not feel the strong nuclear force. There are 6 leptons in total: the electron, the muon, and the tau, each carrying 1 unit of negative charge and 1 neutrino associated with each. The electron and its neutrino form a pair. The muon and its neutrino form a pair. These 3 pairs are sometimes called the 3 generations of leptons, and they are part of the larger framework that physicists call the Standard Model of particle physics. The Standard Model, which took shape through the 1960s and 1970s, describes 3 of the 4 fundamental forces of nature. The strong nuclear force holds quarks together inside protons and neutrons, and holds protons and neutrons together inside nuclei. The electromagnetic force governs light, electricity, and the interactions between charged particles. And the weak nuclear force, the one that matters most for our story, governs certain kinds of radioactive decay, including beta decay, and is the only force through which neutrinos readily interact with anything at all. The weak force is worth pausing on because it is genuinely strange. Unlike electromagnetism, which acts between any 2 charged particles over any distance, the weak force operates only over distances far smaller than the diameter of a proton. It is transmitted by particles called the W and Z bosons, heavy, short-lived carriers of the force, and it has one remarkable property that distinguishes it from every other force. It can change the identity of a particle. Electromagnetism deflects an electron, but it does not change what the electron is. The weak force, by contrast, can turn a neutron into a proton, or an electron neutrino into an electron. It is a force of transformation rather than merely of pushing and pulling. This is precisely why neutrinos are so ghostly. They carry no electric charge, so the electromagnetic force ignores them entirely. They carry no color charge, the property that makes quarks respond to the strong force, so the strong force ignores them too. The only force they feel is the weak force, and the weak force is extraordinarily feeble and short-ranged. For a neutrino to interact with any particle, it has to pass close enough within the operating range of the weak force, and that range is so tiny that the chance of any given neutrino doing so as it passes through matter is almost incomprehensibly small. Think of it this way. A proton is already a tiny thing, about 100 millionth of a centimeter across. The weak force operates over distances roughly 1,000 times smaller than that. A neutrino passing through a block of iron encounters countless billions of protons and neutrons, but to interact with any of them, it would have to pass within that unimaginably tiny range. The vast majority of the time, it does not. It simply continues unimpeded, through the iron and out the other side, and through the ground beneath, and through the planet, and out into space. The three flavors of neutrino, electron, muon, and tau, each participate in the weak force in slightly different ways, always in partnership with their associated charged lepton. When a muon neutrino interacts, it tends to produce a muon. When an electron neutrino interacts, it tends to produce an electron. This is why the Brookhaven experiment was so clear. The muon neutrinos in the beam were simply incapable of producing electrons, no matter how many times they interacted. The Standard Model, in the years following these discoveries, incorporated all three neutrino flavors and described their behavior with extraordinary precision. It was a triumph of systematic thinking. And yet, embedded within it was a small, quiet assumption that would eventually prove to be wrong, an assumption that would take decades to unravel, and whose unraveling would require some of the most extraordinary experiments ever built. The Standard Model assumed that neutrinos had no mass, zero, exactly, not approximately zero, but precisely, fundamentally nothing. It was a clean assumption, mathematically convenient, and for a long time it seemed consistent with every measurement anyone had ever made. That assumption was carrying a tension inside it, a tension that would not stay quiet forever. Picture, for a moment, a square centimeter. The area of a small fingernail, an unremarkable patch of skin. Every second, during the daylight hours, roughly 65 billion neutrinos from the sun pass through that square centimeter of your body. Not 65 billion over a lifetime, not 65 billion per hour. Every second. And at night, when the sun is on the other side of the earth and you are lying in the dark, the same number still arrives, having passed through the entire mass of the planet as if it were open air, emerging from the ground beneath you and continuing upward into space. The Earth does not slow them. The rock and iron of 6,500 kilometers of planet offers no more resistance to a neutrino than a pane of glass offers to light. Less, in fact. To understand where all of these neutrinos come from, we have to go deep into the sun, not to its surface, which is the part we see, but to its center, where the temperature exceeds 15 million degrees Celsius, and the pressure is so extreme that atomic nuclei are stripped bare of their electrons and forced into intimate proximity with one another. This is the solar core, and it is a nuclear furnace that has been burning for 4.5 billion years. The fuel is hydrogen, the product is helium, and the process by which hydrogen becomes helium in the solar core is called the proton-proton chain, because it begins with two protons, two bare hydrogen nuclei, being pressed close enough together that something remarkable can happen. Under ordinary circumstances, two protons would repel each other violently. They both carry positive electric charge, and like charges push apart. But in the core of the sun, the temperatures are so high and the pressures so immense that protons are moving fast enough to come very close together. And when they do, a process takes over that has no analogue in everyday experience. One of the protons undergoes a transformation. through the weak nuclear force that converts it into a neutron. In doing so, it releases a positron and an electron neutrino. The proton and neutron then bind together to form a nucleus of heavy hydrogen called deuterium. This first step is the slowest and rarest in the chain, and it is the one that controls how fast the sun burns through its fuel. Without the weak force, the sun could not shine. The deuterium nucleus then collides with another proton and fuses to form helium-3, a version of helium with 2 protons but only 1 neutron. This step releases energy as gamma rays. Then 2 helium-3 nuclei collide and fuse, releasing 2 protons and forming helium. The complete chain, from start to finish, converts 4 protons into 1 helium-4 nucleus. The helium nucleus is slightly lighter than the 4 protons that went into making it, not by much, but by a measurable amount, and that tiny difference in mass is converted entirely into energy in accordance with the relationship between mass and energy that Einstein described. That energy is what makes the sun shine. But energy is not the only thing released. At several points in the chain, neutrinos are produced. The first step releases one every time it occurs. There are additional branches of the chain, alternative pathways that helium-3 can take, and some of these branches produce higher energy neutrinos. The overall result is a continuous, vast, unstoppable flood of electron neutrinos pouring outward from the solar core in every direction. The sun produces, at any given moment, something in the region of 2 × 10⁻38 neutrinos every second. That is a 2 followed by 38 zeros, a number so large it is almost meaningless to state directly. Those neutrinos travel outward at very nearly the speed of light, and when they reach the Earth, 8 minutes and 20 seconds after leaving the solar surface, or rather after leaving the core, since they cross the entire sun in about 2 seconds, they pour through everything, through the atmosphere, through the oceans, through the ground, through you. This brings us to something beautiful and slightly counterintuitive about the neutrinos from the sun. They are the only direct messengers we have from the solar core itself. The light we see from the sun, the warmth on your skin on a summer day, the light that grows plants and drives weather. That light is not generated at the surface. It is generated in the core, just as the neutrinos are. But light, unlike a neutrino, interacts constantly with matter. A photon of light produced deep in the solar core immediately encounters a dense plasma of charged particles and is absorbed, re-emitted, deflected, absorbed again, scattered in a new direction. The core of the sun is so dense that light cannot travel in a straight line for more than a fraction of a centimeter before being interrupted. The result is that a photon of light produced in the solar core undergoes a random walk, a drunkard's path, bouncing and scattering in every direction, for a very long time before it eventually, by chance, works its way close enough to the surface to escape. The estimates for how long this takes vary depending on exactly how you model the process, but the most commonly cited figure is somewhere between 100,000 and 1,000,000 years. The light arriving at your window this morning left the solar core sometime during the ice ages or earlier. The neutrinos from the same nuclear reactions left the core at almost exactly the same moment as that light and arrived at Earth 8 minutes later. They are, in a very real sense, live images of the interior of the sun, transmitted instantly and without distortion, while the light that was born alongside them is still wandering around inside, centuries from the surface. In the 1960s, a chemist and physicist named Raymond Davis Jr. built a detector deep underground in the Homestake gold mine in South Dakota, specifically designed to catch solar neutrinos. It was an extraordinary thing to attempt. He filled a tank with 100,000 gallons of a dry cleaning fluid called perchloroethylene, a chlorine-rich compound, and placed it a mile underground to shield it from cosmic rays. The idea was that very occasionally a solar neutrino would interact with a chlorine atom and convert it into an atom of argon. Davis would then, every few weeks, carefully flush the tank with helium gas, collect any argon atoms that had accumulated, and count them. The numbers were tiny. In a tank containing roughly 10 to the power of 30 chlorine atoms, Davis expected to catch perhaps one neutrino interaction per day, producing one argon atom. He was right that the interactions were rare. But what he found, when he compared his argon count to the theoretical predictions, was that he was seeing only about 1/3 of the neutrinos the solar models said should be there. Not half, not 2/3, roughly 1/3. This discrepancy, which became known as the solar neutrino problem, persisted for decades. The experiment was repeated, refined, and confirmed. Other detectors, using different methods and different target materials, found the same thing. The sun was producing the right amount of light, the right amount of energy. Everything about it was consistent with the theoretical models. But 2/3 of its neutrinos seemed to be disappearing somewhere between the solar core and Earth's detectors. For 30 years, the mystery sat there, patient and quiet. 1/3 of the expected neutrinos arriving faithfully. 2/3 gone. And the answer, when it finally came, was something that nobody who first proposed it was entirely sure they believed. The solar neutrino problem was not solved by finding an error in the solar models. It was not solved by discovering a flaw in the detectors. It was solved by the realization that the neutrinos were not disappearing at all. They were changing. They were leaving the sun as electron neutrinos and arriving at Earth as something else. This is the phenomenon called neutrino oscillation, and it is one of the most quietly beautiful ideas in modern physics. To understand it, you need to hold two things in your mind at once, and if you are drifting, that is perfectly fine, because the images will come and go gently. The first thing to understand is that there are two different ways to categorize a neutrino. One way is by its flavor, whether it is an electron neutrino, a muon neutrino, or a tau neutrino. Flavor is what you detect when a neutrino interacts with matter. An electron neutrino, when it finally interacts, produces an electron. A muon neutrino produces a muon. The flavor is the identity the neutrino shows to the world when it decides to be seen. The second way to categorize a neutrino is by its mass. It turns out that the three flavor states are not simple, clean things. Each flavor state is a mixture, a superposition of three underlying states that each have a definite, though tiny, mass. These are called the three mass eigenstates, meaning the three states in which the neutrino propagates through empty space with a fixed energy and momentum. They are not the same as the flavor states. Each flavor is a particular blend of all three mass states, and each mass state is a particular blend of all three flavors. Quantum superposition is worth pausing on, because it is genuinely strange, and yet it is also genuinely how nature works. At the quantum level, the level of individual particles, a particle does not have to be in one definite state or another. It can exist in a combination of several states simultaneously, with a certain probability of being found in each one when it is finally measured. This is not a limitation of our knowledge, it is a feature of reality at small scales. The particle is, in a meaningful sense, in several states at once until something forces it to choose. For a neutrino, this means the following. A neutrino born as an electron neutrino in the core of the sun, say during a step in the proton-proton chain, is born in a definite flavor state, but that flavor state is a superposition of three mass states. As the neutrino travels, those three mass states each propagate slightly differently because they each have a slightly different mass and therefore a slightly different energy for the same momentum. The difference in their masses is extraordinarily small, far smaller than the mass of any other known particle, but it is not zero. And over the vast distances that neutrinos travel, even a tiny difference accumulates. Think of it this way. Imagine three waves set off at the same moment from the same point, each with a slightly different frequency. At first, they are all in step, their peaks and troughs aligned. But as they travel, the small differences in their frequencies cause them to drift slowly out of alignment. After a while, they are out of step by half a cycle, then back in step, then out again. The pattern of alignment oscillates as the waves travel, and the oscillation repeats over a distance determined by the differences in the frequencies. For neutrinos, the three mass states are like those three waves. As they travel, they drift out of step with one another, and the flavor of the neutrino, which is determined by the particular combination of mass states at any given moment, rotates as a result. An electron neutrino, after traveling a certain distance, might find itself predominantly a muon neutrino. After further travel, it might rotate toward a tau neutrino and then back toward an electron neutrino, cycling through the possibilities in a slow, repeating pattern. The period of this oscillation, the distance over which the flavor completes one full cycle, depends on the differences between the masses of the three mass states and on the energy of the neutrino. For solar neutrinos, the relevant oscillation length is comparable to the distance from the Sun to the Earth. This means that solar neutrinos, by the time they arrive at our detectors, have had ample opportunity to oscillate away from the electron neutrino flavor they were born with. And because the early detectors, like Raymond Davis's chlorine tank, were sensitive only to electron neutrinos, they missed the muon and tau neutrinos that had been electron neutrinos when they left the Sun. The 2/3 of neutrinos that seemed to be missing were not missing at all. They had simply changed their identity during the journey. The experimental confirmation of this came in 2 stages, both of which earned Nobel Prizes. The first was at the Super Kamiokande detector in Japan, buried deep in the Mozumi zinc mine in the Japanese Alps, about 1 kilometer underground. Super Kamiokande, which we will visit in more detail in the next chapter, announced in 1998 that it had strong evidence for oscillation in neutrinos produced by cosmic rays hitting the Earth's atmosphere. These are called atmospheric neutrinos, and they come in 2 flavors, electron neutrinos and muon neutrinos. The Super Kamiokande team found that muon neutrinos arriving from directly overhead, having traveled only about 20 kilometers through the atmosphere, were present in the expected numbers. But muon neutrinos arriving from below, having traveled through the entire Earth, about 13,000 kilometers, were significantly depleted. They had oscillated into tau neutrinos during the journey. The longer the path, the more time for the flavor to rotate. The second and decisive confirmation came from the Sudbury Neutrino Observatory in Canada, deep in a nickel mine in Ontario. The Sudbury detector had a crucial advantage over earlier solar neutrino experiments. It could detect all 3 flavors of neutrino, not just electron neutrinos. It did this by using heavy water in which the ordinary hydrogen atoms are replaced by deuterium, heavy hydrogen, as its detection medium. Heavy water allows certain reactions that ordinary water does not, and one of those reactions is sensitive to any flavor of neutrino, not just the electron kind. When the Sudbury team, led by Arthur MacDonald, published their results in 2001, they showed 2 things simultaneously. First, the total number of neutrinos arriving from the Sun, counting all 3 flavors, matched the theoretical predictions from solar models perfectly. Second, only about 1/3 of those neutrinos were arriving as electron neutrinos. The rest had oscillated into muon and tau neutrinos during the 8-minute journey from the solar core. The solar neutrino problem was solved. The solar models were right. Davis's detector was right. The neutrinos were right. They had simply been changing flavor in transit, and the early detectors had only been able to see one flavor. But the solution carried a consequence that shook the foundations of particle physics. Neutrino oscillation is only possible if the 3 mass states have different masses. And if they have different masses, at least 2 of them, and possibly all 3, must be non-zero. The standard model had said firmly the neutrinos were massless. That assumption was wrong. Takaaki Kajita of Super Kamiokande and Arthur MacDonald of Sudbury shared the 2015 Nobel Prize in Physics for the experimental discovery of neutrino oscillation. It was a recognition not just of a technical achievement, but of a genuine revision to the most successful theory in the history of particle physics. The neutrino had mass. Tiny, almost unimaginably small, at least 1,000,000 times lighter than the electron, which is itself already an extraordinarily light thing. But not zero. The ghost had weight. Barely any, but some. And that small, stubborn fact opened a door to questions that physics is still walking through. Because the neutrino interacts so rarely with matter, catching one requires not just patience, but scale. The detectors built to hear the whisper of a neutrino are among the most remarkable structures human beings have ever assembled. They are built underground, in darkness, in silence, using materials of extraordinary purity. And they are designed to detect flashes of light so faint that the detectors themselves must be shielded from the natural radioactivity of the rock around them, and even from the radioactivity of the glass in the light sensors. Building one is an exercise in eliminating every other possible source of signal until only the neutrinos remain. Super Kamiokande sits a kilometer underground in the Mozumi zinc mine in the Gifu prefecture of Japan, buried beneath the Japanese Alps. The mine was chosen not for its zinc, but for the mountain above it. A kilometer of solid rock that acts as a shield, absorbing the constant rain of cosmic rays that would otherwise overwhelm any sensitive detector at the surface. Cosmic rays are high-energy particles from space that constantly bombard the Earth's atmosphere, and they produce a background of secondary particles that would mimic neutrino signals if allowed through. The rock filters them out, leaving the neutrinos which pass through the mountain as though it were not there. The detector itself is a cylinder of stainless steel, roughly 50 meters across and 40 meters tall, about the size of a large cathedral. It holds 50,000 tons of ultra-pure water. Ultra-pure means exactly that. The water inside Super Kamiokande has been filtered and purified to a degree that makes it essentially free of dissolved minerals, organic molecules, and any other contaminant. Ordinary tap water contains trace amounts of radioactive atoms. Potassium-40, for instance, that would produce false signals. The water in Super Kamiokande is so clean that it is, in a sense, one of the purest substances in the world. The inner surface of the cylinder is lined with approximately 11,000 photomultiplier tubes, large glass spheres, roughly 50 centimeters across, each one a device that can detect a single photon of light and amplify that detection into an electrical signal. They face inward, staring into the dark water, waiting. The density of these sensors is high enough that if a flash of light occurs anywhere in the water, multiple sensors will detect it, and the pattern of detections will allow physicists to reconstruct where the flash originated and what direction the particle that caused it was moving. The detection principle is called Cherenkov radiation. This is worth understanding because it is a beautiful piece of physics. In vacuum, nothing travels faster than light. But in a medium like water or glass, light itself slows down. It travels at roughly 3/4 of its vacuum speed in water. This is why water refracts light, bending it at the surface. Now, a neutrino interaction can produce a charged particle, an electron for instance, that carries away a great deal of energy. If that electron is moving faster than the slowed down speed of light in water, something interesting happens. The electron disturbs the electromagnetic field of the water molecules as it passes, and those disturbances, because the electron is moving faster than the light they produce, stack up into a coherent wavefront, the optical equivalent of a sonic boom. The result is a faint blue glow, a cone of light spreading outward from the particle's path. This is Cherenkov radiation. It does not violate the principle that nothing travels faster than light in vacuum. The electron is still moving slower than light in vacuum. It is only moving faster than light moves through water. This is entirely permitted by the laws of physics. It is a difference in medium, not a breaking of the universal speed limit. The Cherenkov glow is faint, extraordinarily faint, but the 11,000 photomultiplier tubes in Super Kamiokande can detect it. When a neutrino interaction occurs inside the tank, the resulting Cherenkov cone sweeps across the wall of sensors and the pattern of lit sensors. A ring of light, like the shadow of a cone projected onto a sphere, tells the physicists what kind of particle was produced, how energetic it was, and what direction it was moving. From that, they can work backwards to infer the properties of the neutrino that caused it. Super Kamiokande detects a handful of neutrino events per day against a background of nothing. In a tank of water in the dark, a kilometer underground, a handful of events per day is enough to do physics with. It was enough to discover neutrino oscillation. Then there is Ice Cube. If Super Kamiokande is a cathedral, Ice Cube is a continent. It sits at the South Pole, and it uses not water but ice. Specifically, the ancient glacial ice of Antarctica, which is extraordinarily transparent at depth below 2 kilometers, where the air bubbles that make shallower ice opaque have long since been compressed out of existence. Between 2005 and 2010, a team of physicists drilled 86 holes in the ice, each one 2.5 kilometers deep, using a hot water drill to melt a column about 60 centimeters across. Into each hole, they lowered a string of 60 sensors, each one a glass sphere encasing a photomultiplier tube, then allowed the water to refreeze around them. The result is a cubic kilometer of Antarctic ice, a block, roughly a kilometer on each side, instrumented with 5,160 sensors, each one watching for Cherenkov light from neutrino interactions in the ice. Ice Cube is sensitive to neutrinos of much higher energies than Super Kamiokande, not the gentle, low-energy neutrinos from the sun or from nuclear reactors, but the high-energy neutrinos produced by violent events in distant galaxies, jets from supermassive black holes, the remnants of exploded stars, perhaps sources we have not yet identified. In 2013, the Ice Cube collaboration announced the detection of the first confirmed high-energy neutrinos of cosmic origin, neutrinos arriving not from the sun or from the atmosphere, but from somewhere far beyond our galaxy. The team gave the two highest energy events playful names, Bert and Ernie. They carried energies roughly 1,000,000 times higher than the neutrinos produced in the sun, suggesting they had been accelerated by some of the most energetic processes in the universe. Where exactly they came from remains, in many cases, an open question. Pinpointing the sources of cosmic neutrinos is difficult, because the neutrino's path through space is a straight line, but the sources are faint and distant, and background events are numerous. But the detections were real, and they opened a new window onto the high-energy universe. Both of these instruments, Super Kamiokande in its mountain, Ice Cube in its ice, represent a philosophy of science that is worth admiring. They are not built to catch something common. They are built to catch something that almost never happens by making the arena large enough and quiet enough that the rare event, when it occurs, stands out. They are temples of patience, vast, silent, cold, watching. There are others, the Sudbury Neutrino Observatory, now refurbished and expanded into a new experiment called SNO+, which has replaced the heavy water with a liquid that can also detect neutrinos from the decay of radioactive elements deep in the Earth. There is Borexino, deep in the Gran Sasso mountain in Italy, which uses a sphere of extraordinarily pure liquid scintillator, a substance that flashes when a charged particle passes through it, and has made the most precise measurements of solar neutrino fluxes ever achieved, detecting even the rarest branches of the proton. There are detectors planned and being built that will dwarf even Ice Cube in scale. all of them listening, all of them waiting, in the dark, in the ice, in the deep rock of mountains, surrounded by the constant invisible flood of particles that pass through everything and notice nothing. These instruments have been tuned to the faintest possible signal, the whisper of a neutrino, choosing, just once, to say hello. On the 23rd of February 1987, a young Canadian astronomer named Ian Shelton was working at the Las Campanas Observatory in Chile, developing a photographic plate he had taken of the Large Magellanic Cloud, a small companion galaxy to our own Milky Way, visible from the southern hemisphere as a faint smudge in the sky. When he held the plate up to examine it, he noticed a bright spot that had not been there the night before. He went outside and looked up with his naked eye, and there it was, a new star, visible without a telescope, in a galaxy 160,000 light-years away. It was the closest supernova to Earth since 1604, when Johannes Kepler had observed one in our own galaxy. Astronomers around the world turned their instruments toward it within hours. It would be studied intensively for years, and it would teach us more about the death of massive stars than any event in the history of modern astronomy. But the most significant thing about supernova 1987A was not seen through any telescope. It was recorded, hours before Ian Shelton noticed his bright spot, by 3 separate neutrino detectors on different continents. To understand why, we need to understand what happens when a massive star dies. A star like our Sun will, when it eventually exhausts its hydrogen fuel in about 5 billion years, expand into a red giant, shed its outer layers gently into space, and leave behind a dense, slowly cooling remnant called a white dwarf. It will not explode. It will not produce a supernova. It will simply fade. But a star significantly more massive than the Sun, 8 times the mass of the Sun or more, has a different fate. It burns through its hydrogen, then its helium, then carbon, oxygen, neon, and silicon in a sequence of increasingly rapid fusion stages, each one producing heavier elements and releasing less energy per step. The core accumulates iron, and iron is where fusion stops. Iron is, in a very specific sense, the most stable nucleus. Fusing 2 iron nuclei together does not release energy. It requires energy. It requires energy. The iron core cannot burn. It simply sits there, growing heavier as the shells of silicon above it continue to fuse and rain iron downward. The core grows. Until one day, in a fraction of a second, it reaches a critical point. That critical point is related to a limit. Physicists call it the Chandrasekhar limit, of about 1.5 times the mass of our Sun. This is the maximum mass that a core of electrons and ions can support against gravity by the pressure of its own electrons. When the iron core exceeds this mass, the electrons can no longer hold it up. The core collapses. What happens next is almost beyond imagination in its speed and violence. The core, which was roughly the size of Earth, collapses to a sphere roughly 20 kilometers across in less than a second. As it collapses, the pressure becomes so extreme that protons and electrons are forced together through the weak nuclear force to form neutrons, releasing an enormous burst of electron neutrinos in the process. The core becomes almost entirely neutrons, packed together at the density of an atomic nucleus, and the collapse halts abruptly as the neutrons resist further compression. The halt is so sudden that the infalling outer layers of the star, still rushing inward at 1/4 of the speed of light, bounce off the rigid neutron core and reverse direction, sending a shockwave outward through the star that eventually tears it apart entirely. The visible explosion, the supernova flash, is this shockwave breaking through the stellar surface and illuminating the surrounding gas. It is a spectacular event, but in terms of energy, it is almost a footnote. Because 99% of the energy released in a core collapse supernova is carried away not by light, not by the shockwave, but by neutrinos. The collapse releases a quantity of gravitational energy equivalent to roughly 300 times the total energy the Sun will radiate across its entire 10 billion year lifetime. And almost all of that energy, within seconds, leaves the collapsing core as neutrinos, produced by the continuous conversion of protons and electrons into neutrons throughout the dense hot proto-neutron star. The neutrino burst from a supernova lasts about 10 seconds. In those 10 seconds, the dying star emits more neutrinos than all the stars in the observable universe combined have emitted in the past 10 years. It is the most intense burst of neutrinos in the universe, short of the Big Bang itself. For supernova 1987A, that burst was detected by 3 instruments: the Kamiokande 2 detector in Japan, the predecessor to Super Kamiokande, the Irvine, Michigan, Brookhaven detector in a salt mine in Ohio, and the Baksan underground scintillation telescope in the Caucasus Mountains in Russia. Kamiokande 2 recorded 11 neutrino events. The Ohio detector recorded 11 neutrino events. The Ohio detector recorded 8. 24 events in total, arriving in clusters spanning about 12 seconds on 3 separate continents from a star dying in another galaxy. 24. That is all. From a burst that produced more neutrinos than the human mind can meaningfully picture, 24 of them interacted with the detectors of Earth. The rest passed through as though the planet were not there. The neutrinos arrived at Earth roughly 2 to 3 hours before the visible light from the explosion. This is not because neutrinos travel faster than light. They do not, or at least they travel at a speed so close to the speed of light that the difference is immeasurable. The reason the neutrinos arrived first is that they were produced in the core of the star and escaped immediately, passing through the stellar envelope as though it were empty space. The shockwave that would eventually produce the visible explosion took hours to travel from the core to the stellar surface. The light could not leave until the shockwave broke through. The neutrinos were already gone. The tiny spread in the arrival times of those 24 neutrinos, a spread of about 12 seconds during which they arrived in a cluster, also told physicists something useful. If neutrinos had significant mass, the heavier ones would travel slightly slower than the lighter ones, and a burst that left the supernova simultaneously would spread out during the 160,000-year journey to Earth, arriving over a longer period. The fact that all 24 arrived within 12 seconds placed a very tight upper limit on how much mass the neutrino could have. Not zero. The oscillation evidence would later confirm that, but very, very small. The supernova gave physicists a ruler of a kind to measure the neutrino's mass, even if it could only tell them it was smaller than a certain value. The star that exploded was catalogued as Sanduleak-69202, a blue supergiant about 20 times the mass of the Sun, sitting in the Large Magellanic Cloud. It had been there, burning quietly, for millions of years before that February night. The neutrinos it released in its final second of collapse had been traveling through space for 160,000 years before they reached Earth. They passed through the detectors in Japan, Ohio, and the Caucasus at 7,035 in the morning, universal time. They passed through everything else on Earth at the same moment, through the oceans, through the sleeping and waking bodies of every person on the planet, through the ice of the poles, through the bedrock, through everything. All of them. Most of us did not notice. None of us felt it. The neutrinos, as always, left no trace of their passage. But the instruments, patient and dark and listening, caught the faintest echo of that ancient catastrophe, and from those 24 small signals, an entire field of astronomy was born, neutrino astronomy, the study of the universe through its most elusive messengers. Before the universe was a second old, it was filled with neutrinos. In the first fractions of a second after the Big Bang, the universe was so dense and so hot that all particles were in constant, rapid interaction with one another. Neutrinos were produced continuously, collided with other particles, were absorbed and re-emitted, existing in a state of thermal equilibrium with everything else. Then, when the universe was about 1 second old and had expanded and cooled to roughly 10 billion degrees, something changed. The density dropped just enough that the weak force interactions keeping neutrinos in contact with the rest of the matter became too rare to maintain equilibrium. The neutrinos decoupled. They stopped interacting and began to travel freely through the expanding universe, carrying the thermal imprint of that moment with them. Those relic neutrinos are still here. They have been cooling ever since, as the universe expanded around them, their energies dropping with each passing billion years. Today, they permeate all of space at a temperature of about 1.9 degrees above absolute zero, barely above the coldest anything can possibly be. They are present everywhere, at a density of roughly 330 per cubic centimeter throughout all of space, not 330 in a special place, everywhere. In your room right now, in the space between galaxies, in the void between stars, everywhere, always, a faint and ancient background of neutrinos from the first second of time. We have not directly detected them. They are too cold, too low in energy to interact with anything in our current detectors, but we know they are there. Their gravitational influence on the large-scale structure of the universe is measurable. The way galaxies cluster and form filaments and voids across the cosmos is subtly shaped by the presence of a sea of light, ancient particles, and our models of how that structure forms only work if we include them. They are invisible, and yet their shadow is written across the universe at the largest scales. This brings us to one of the deepest open questions in physics. We know from oscillation experiments that at least 2 of the 3 neutrino mass states have non-zero mass. But we do not yet know the actual values of those masses, only the differences between them. We know that the differences are very small. The heaviest neutrino mass state is probably no more than 1/10 of an electron volt. For comparison, an electron has a mass of about 500,000 electron volts, making the neutrino at least 5 million times lighter, but the precise values remain unmeasured. This matters enormously for cosmology. Neutrinos, though individually feather-light, exist in such vast numbers that their collective mass is a significant fraction of all the ordinary matter in the universe. The exact value of their mass influences how the universe's large-scale structure evolved, how quickly matter could clump together under gravity in the early universe, how the filaments and walls and voids of the cosmic web took shape. Knowing the neutrino mass precisely would allow cosmologists to sharpen their models of how everything came to be arranged the way it is. Then there is a deeper question still. A question that sits at the very heart of why anything exists. The universe, as best we can tell, is made almost entirely of matter rather than antimatter. This is strange because the processes of the Big Bang should have produced equal quantities of both, and matter and antimatter annihilate each other on contact. If they had been produced in equal amounts, they would have annihilated each other completely, leaving nothing but light. The fact that we are here, that matter exists at all, means something must have tipped the balance very slightly in favor of matter over antimatter in the early universe. The nature of that imbalance is one of the greatest unsolved problems in physics. Neutrinos may hold part of the answer. This depends on a question that has not yet been resolved, whether the neutrino is its own antiparticle. For most particles, the particle and its antiparticle are distinct. The electron is different from the positron, the proton is different from the antiproton. But for a neutral particle, it is at least possible that the particle and its mirror image are identical, that the neutrino, when you flip it and look at it in an antimatter mirror, looks exactly the same as it did before. A particle with this property is called a Majorana particle, after the Italian physicist Ettore Majorana, who first explored the theoretical possibility in 1937. If neutrinos are Majorana particles, a remarkable consequence follows. It would mean that a process called neutrinoless double beta decay, where two beta decays happen simultaneously inside a nucleus and no neutrinos are emitted at all because the two neutrinos that would have been produced annihilate each other, should be possible. Physicists are searching for this process in a number of experiments around the world, including one called CAMLAND, Zen in Japan, which uses a sphere of xenon-rich liquid inside the Super Kamiokande tank. So far, it has not been observed. But the search continues because finding it would tell us something profound, that the neutrino is its own mirror, that matter and antimatter are, in the neutrino's case, the same thing, and that symmetry, or the breaking of it, may be connected to the reason that the universe chose matter over antimatter when it was very young. There are heavier cousins of the neutrino that some theories predict. Very heavy, very neutral particles called sterile neutrinos, which would interact even more rarely than ordinary neutrinos, if at all. Some cosmologists have suggested that these hypothetical heavy neutrinos might be connected to dark matter, the invisible substance that makes up most of the massive galaxies but has never been directly detected. These are ideas at the frontier, speculative in the best sense of the word, meaning they are taken seriously and tested carefully, but not yet confirmed. And beneath all of this, there is still the most basic question of all: why three? Why three generations of leptons? Why three flavors of neutrino? The standard model accommodates 3 generations but does not explain why there are 3 rather than 2 or 4 or 17. It is a pattern that the theory describes but does not derive. The universe chose 3, and we do not yet know why. These questions are still open. They will likely occupy physicists for decades to come, perhaps longer, and there is something restful in that, if you let it be. The universe is not finished being understood. There are still doors that have not been opened, still corridors that have not been walked. The neutrino has been leading us down one of those corridors for nearly a century now, and every time we think we have caught up with it, it turns a corner and shows us something new. But tonight, the questions can rest. Tonight, the neutrinos themselves are the thing worth sitting with. Right now, as you lie in the dark, somewhere in the region of 65 billion solar neutrinos are passing through every square centimeter of your body that faces the sun, and because the sun is below the horizon, they are coming up through the earth, through the ground beneath your building, through the floor, through the mattress, through you, and continuing upward and outward into space. They have been traveling for 8 minutes and 20 seconds since they were born in a nuclear reaction at the center of the sun, 150 million kilometers away. They have passed through the full diameter of the Earth in less time than it takes a nerve signal to travel from your fingertip to your brain. They have not slowed. They have not scattered. They have not noticed anything in their path. And alongside those solar neutrinos, there are the relic neutrinos from the Big Bang. 330 per cubic centimeter everywhere, drifting through the room at speeds so close to the speed of light that the difference is immeasurable, carrying the thermal memory of the first second of the universe, 13.8 billion years ago. They are the oldest things that move. They were there before the first star formed, before the first atom, before light could travel freely through the young cosmos. They have been crossing the universe ever since, cooling slowly, spreading thin, present in every corner of space that has ever existed. They pass through you without harm. They leave no trace. They carry no message meant for you, and yet there is something in their passage that feels, if you let it, like a kind of company. It is full, almost incomprehensibly full, of these small, patient, indifferent things, moving through everything, connecting the solar core to the ground beneath your bed, connecting the first second of time to this particular moment, in this particular room, where you are lying still, and the night is quiet and the day is already growing distant behind you. You have been threaded through 1 trillion times by particles that have crossed the solar system, by particles that have crossed the galaxy. by particles born in the death of a star 160,000 light years away, passing through on their way to somewhere else, carrying nothing that can hurt you and nothing that can stop them, ancient and patient and utterly, peacefully free. The questions about their mass, their nature, their role in the origin of matter, those questions will still be there tomorrow, waiting for the people whose job it is to ask them. They do not need you tonight. What needs you tonight is rest. The weight of whatever you carry today can set down now. The neutrinos will continue their passage without any help from you, through the dark and through the earth and through the silence, as they have been doing since long before there were any humans to wonder about them, and as they will continue to do long after the last question about them has been answered. The night is soft around you. The dark is patient. Somewhere above the ceiling, through the roof, through the air, through the thin shell of atmosphere and into the open quiet of space, the neutrinos are streaming outward, away from the sun, away from the galaxy, into the vast and ancient dark. And so we leave it there. The stars are still burning. The neutrinos are still passing through. The day is already far behind you. Drift now, if you are ready. Sleep well.